All right, so this is a really cool problem because now instead of 1D, where the objects are only moving left or right or up and down, we're going to start talking about 2 dimensions. So we're still going to focus on the same kind of properties. So if it's a perfect inelastic collision, momentum is conserved, not energy. If it's a perfect elastic collision, momentum will be conserved and mechanical energy. In this case, we'll start with the easiest one possible. Inelastic is going to be easier, just like before, because when they collide, they're going to stick together. So that instead of having 2 variables at the end, we only have 1. So we could just use momentum. Pretty much when you have collisions, we know that initial momentum is going to equal final momentum. Now, since it's in 2D, we're going to break it up into its x component and into its y component. So we want to make sure that both initial momentum and final momentum, we want to break it up into its x and y. We're going to first start off easy, meaning that the cars are going to be either all x or all y. And then we'll kind of build up into a harder problem when you do actually have cars hitting at an angle other than just 90 degrees. So in this case, we have a 950 kilogram car, and it's going, let's say, 16 meters per second. And then car B is moving at 21 meters per second. I wrote plus, but it's not necessary because in 2D, you could kind of set the direction that you want. I'm just going to go with convention. Right is positive, up is positive. But when we start doing angles, you just have to start keeping in track. Are they in the same direction or in the opposite direction? And you'll see when we get there. So let's first focus on car A. So let's look at the x direction. And with momentum, remember, it's just mv. So remember, momentum is inertia motion, or inertia in motion, mass times velocity. So in the x direction, we're going to still do the same thing. Momentum in the x is just mass times velocity. But we want to make sure our velocity is in the correct direction. In this case, the plus 16 is only going in the x direction. So we could just multiply it. 950 kilograms times 16 meters per second will give us our momentum. So 950 times 16 gives us 15,200, and this was kilograms, and this was meters per second. And this is in the positive direction. Okay, so that's how much momentum car A has in the x direction, right or left. In the y direction, though, it's not moving up or down, so the velocity is 0. But I still want to do it just for the sake of doing it. So in the y direction, the car A has 0 momentum. It has all its momentum in x. Now for car B, it's the exact opposite. It's going up and down, so it has nothing going left and right. So its mass is multiplying 0 over here. So you get 0 kilograms meters per second. But all its velocity is in the y direction. So 1,300 kilograms times positive 21 meters per second. And you get 27,300 kilograms meters per second. So for car A, all of its momentum is in x. For car B, all of it's in y. But we want to know the initial momentum, pi. So we're going to do it for all this. So you add these two together. 15,200 plus 0 gives us 15,200 kilograms meters per second in the x direction. Let me just kind of, in parentheses, in x axis. And then the other one is 0 plus this, so you get 27,300 kilograms meters per second in y-axis. Now, remember, initial momentum is equal to final momentum. So if the initial momentum is this and this, then final momentum is the same thing. So the final momentum in the x direction is also 15,200. The final momentum in the y direction is that. We can actually figure out how fast it's going. So after car A collides with car B, let me kind of draw my best collision right here. So here's B, here's A. Now they're together, they're stuck together. So remember, inelastic collision means they're stuck together. So now their mass is mass of 1 plus mass of B, which is in this case 1300. So you get a total mass of, I believe, 2250. So here, remember, before we had 2, but now we only have 1. So in the x direction, PF in the x direction is equal to 15200. So it's equal to MV. So we can just plug in the mass, 2250 kilograms. Velocity equals 15200 kilograms meters per second. We're going to divide out kilograms, right? And we're going to be left with velocity. So divide both sides by 2250, 15,200 divided by 2250, and we're left with 6.75 continue meters per second. And this is in x. Oops. Let me just erase it. X axis. Do the same thing for the y. And I'm not going to set it up as much. So it'll be 2250, same mass, is equal to, in this case, 27,300. And, oh, I forgot the v on this side. So you're going to solve for v. So do the same thing, but in the y direction, 27,300 divided by 2250. And we get 12.13, repeating on the 3 meters per second. This is in y-axis. So after the collision, this object is moving Vy is equal to 12.13, and then moving this direction, the Vx, which is 6.75. And we will combine them. So we have one leg of a right triangle, other leg of a triangle, so we want to find this one. I usually like defining this as the angle, but you could do whatever you want. In this case, it makes sense. Oh, actually, sorry. We could even do this one. So let's try to find this one, but this right angle is going to be this. So up is going to be 12. Vx is going to be this way. In our right triangle, this is the theta we want, but I'm going to try to solve for this one. I'll try to get to it when I show you. So here we go. So this is just a Pythagorean theorem. You have this squared plus this squared will give you hypotenuse squared. So I'm going to go Vy squared plus Vx squared will give us the V theta, the velocity at the angle, squared, and we just solve for it. So 12.13 squared plus 6.7, I'm going to round up, 6.67 squared. And then we're going to take the square root of that, and we're left with 13. So V theta is 13.89 meters per second. So we got velocity at the angle, and we can also find the angle too. So remember, this is a tangent is opposite over hypotenuse. So let me change my color so we can follow around. Tangent of theta in this case is opposite over adjacent. In this case, Vx over Vy. So just plug in those values. 6.75 divided by 12. Oh, let me redo that. 6.76. Sorry, since I rounded, this should be a 6. 6.76 divided by 12.13. And you want to do the inverse tan of that. And I get an angle of 29.13. Now this is of this angle right here. Usually you want to reference the horizontal. So I'm going to just take the complementary angle. So minus or 90. And I get about 60.8. So this angle is the one I want to define it at. So it's 13.89 at 60.8 7 degrees above horizontal. So that's the proper way of defining this velocity. Pick a reference place. In this case, it's going to be horizontal. So it's 13.89 meters per second, and it's 60.87 degrees above horizontal. So hopefully that helps out. Remember, this is a very simple problem because A only goes in the X and Y direction, X direction, and B only goes in the Y direction. So we don't have to worry about sine and cosine over here. In our next problem, we will.